In this lecture, we are going to cover the least squares estimator and present a more convenient form for its implementation, namely the recursive form to which we already hinted in the previous lecture. It turns out that a very useful feature of the least squares estimator is that we can rewrite it in a recursive form which is suitable for sequential rather than batch processing. Obviously, we don't want to have to reprocess the entire data set as you accumulate more and more data. In this case, we can interpret k as discrete time index. When we obtain the observation number k plus 1 or at time k plus 1, we can partition the cumulative set of observations, z super k plus 1, that's a big stacked vector, into z super k and z at k plus 1. Similarly, we have the h super k plus 1, this is a big stacked matrix, into the previous one, h super k, and the latest h at k plus 1. As far as the weighting matrix in the cost function, or we have seen this is also the covariance matrix of the noise under the maximum likelihood model, R super k plus 1 will have a R super k block here, which really is made up of k blocks or sub-blocks, and the last block number k plus 1, that's R at k plus 1. First, we are going to rework the covariance. Actually, the inverse covariance has a nice recursion. What we had before was the expression for the covariance associated with the estimate. That was pk plus 1. We write the inverse of it, and this is hk plus 1 transpose rk plus 1 inverse hk plus 1. And now we substitute for hk plus 1 its partition into h super k and h at k plus 1, because this is transposed, each of these blocks has to be transposed as well. And big R super k plus 1 is partitioned into R super k and R at k plus 1. We have an inversion here, and this is just a transpose of the first matrix. Now, we can look at this as a quadratic form, as if each of these blocks was a scalar and carry out the multiplications as long as we don't change the order, because each is really a matrix block. So we have a 1-1 term in this matrix to be inverted, and a 2-2 term. That's a very easy inversion because it's a diagonal, a block diagonal. So we have the first one, that's 1-1, multiplied with the first term here and the first term here. So that's an hk inverse rk hk prime rk inverse hk. That's for the 1-1 term, and the 2-2 term is h at k plus 1 prime r at k plus 1 inverse h k plus 1. So term 2, term 2-2, term 2. If we look at this, what we see here is that the first term is really what we had before as p at k. So the inverse of the estimation covariance at k plus 1 is the inverse of the covariance at k plus what can be called the new information about the parameter obtained from the observation. And this is again the additivity of the information, which we have seen it in a scalar case before. Now it's a general, much more general matrix case, because these observations, the one at k plus 1 and the previous ones, are all independent of each other, in which case we have this additivity property of the information. So, to summarize this, the information in the sense of Fisher, that is the inverse covariance, and we have this Fisher information concept from the Cramer-Rao lower bound. So this information at k plus 1 equals the sum of the information at k and the new information about x obtained from z at k plus 1. And we have this additivity property of the information because first property is the problem is static, the parameter is fixed, which means we can accumulate information about the same quantity, And the second is that the observations, as indicated before, are independent. Now, if we use the matrix inversion lemma that we have seen in chapter 1 when we summarize linear algebra, we can rewrite our recursion for the inverse covariance as a recursion for the covariance. And this becomes pk plus 1 would be the inverse of pk inverse plus hk plus 1 prime rk plus 1 inverse hk plus 1. And now with the matrix inversion lemma, this becomes pk minus pk hk plus 1 prime, open the brackets here, hk plus 1 pk hk plus 1 prime plus rk plus 1, this whole thing inverse, hk plus 1 pk. So we can see now a second form for the covariance equation, one for its inverse, there is a recursion, then there is a recursion for the matrix itself. Now, what we would like is to denote a couple of matrices with some notations which will have major meaning in a very short while. Namely, we denote sk plus 1 the matrix H pH prime plus R, and the second one W as a P H prime S inverse. They will have interpretations. The first one turns out that it will be the covariance of the residual, which we have to define still, and the second one is the parameter update gain, which is like a filter gain, as you will see later in the context of dynamic state estimation, the Kalman filter. Now, we go back to the recursion of the covariance, and we can write the most compact form of the covariance recursion. Equation 7 can be rewritten as pk plus 1 equal I minus wh times pk. This is a compact form, but if you look at it, it does not look symmetric, even though it is symmetric. But if you carry out the multiplications in the order that they are indicated here, you might end up, because of just a round of errors, with a matrix that slightly lacks symmetry, and this is not a good idea. And we have a second version of it. Pk plus 1 is pk minus ws w transpose, which is already looks symmetric, and this is guaranteed to give the right result. Remember, the covariance matrix has to be symmetric. Now, we will next obtain the recursion for the estimate. The batch estimate at time k plus 1, x hat k plus 1, was obtained as p at k plus 1, h super k plus 1 prime, r super k plus 1 inverse, z super k plus 1. And this was really h prime r inverse with index k plus 1 h. So what we have here is just a simplified notation that's more convenient for the batch estimator. Now, we'll leave the pk plus 1 as is. We use now blocks for the h super k plus 1. First block is hk, h superscript k, second is h at k plus 1 or h of k plus 1. The r super k plus 1 again is broken down into blocks rk and r at k plus 1, block diagonal, and the z, which is a big stacked vector, it's zk plus 1, on top of it we'll have z super k, at the bottom z at k plus 1. And again, we have this multiplication that can be carried out very easily, and the first term, one term, with the one term here and the one term here, yields p at k plus 1, h super k transpose r super k inverse, z super k. The 2 term, with the 2 term from second from here and second from here, pre-multiplied by pk plus 1 is pk plus 1, hk plus 1, rk plus 1 inverse, there's a transposition here obviously, and z at k plus 1. So what we have now is an expression that one more modification will bring it into an obvious recursive form. So what we are going to do is we'll use for pk plus 1 the most compact form of its recursion in terms of pk, namely pk plus 1 is I minus wk plus 1 hk plus 1 times pk, to be continued the multiplication by hk prime rk inverse zk. Here we are using the replacement notation for pk plus 1, hk plus 1 prime, rk plus 1 inverse as wk plus 1. That what will multiply zk plus 1. And finally, we have now the recursion that the estimate at k plus 1 is a matrix I minus wh, the estimate at k, plus a w times the new measurement. So this is clearly a recursion, even though it is not yet in the most convenient form. But the new estimate is the previous estimate plus something multiplying the latest measurement, and that something is called the gain. We can rewrite it one more time by saying that the new estimate equals to the old estimate plus w times z minus h x hat. And this is the last and final form, because what we have now, new estimate is old estimate plus gain times a correction term. So the gain multiplying this residual, the correction term really is the gain times the residual, and the residual is the difference between the observation at k plus 1 and what we would have predicted that we will obtain at k plus 1, namely hk plus 1 times our best estimate for x from the previous time, which is x hat k. So this is the residual times the gain is the correction term. Obviously, we have a recursive scheme, we have to initialize it. The way we can initialize it, we will have to use a batch technique on a small number of the initial measurements, or by using an a priori initial estimate and associated covariance. This will be discussed in more detail in the context of dynamic state estimation, but typically we can use a small batch, the minimum number of measurements initially, to start up our estimation scheme and then continue recursively. Now, there was a term that was introduced, the sk plus 1, which was called covariance of the residual. Now that we know what the residual is, we can look at the expected value of the product zk plus 1 minus hk plus 1 h hat k times itself transposed, and it can be very easily shown that this is what we defined as sk plus 1, and this is an exercise that is highly suggested that you go through it. Okay, we can use the least squares and incorporate into it prior information. And the way to do it is as follows. We go back to the simple example of the sample mean, where we have noisy observation of a constant scalar x, zi is x plus wi, k such observations. If we look at the least squares, for k measurements, we can define the stacked matrix H super k really is a vector of ones, there are k ones, a single column, and R super k will be a diagonal matrix with each element being sigma square, because this is the covariance matrix of the stacked noises. So we assume them zero mean and independent and with same variance sigma square. So I is the identity matrix of dimension k by k. Now we can use the batch form of the estimator. X hat k, this is the hk prime rk inverse hk inverse, hk prime rk inverse z super k, and we can write down individually the hk prime, and now it's a row of ones, the r super k is an identity, k by k times sigma square inverted. Now hk is a column vector, the whole thing inverted, and then we have the hk prime, again r inverse and z. Carrying out these multiplications, we retrieve nothing but the old sample mean. So it's obvious that for this problem the least squares does give what we already know, the same result. So the variance of this estimate, assuming the WI to be IID as indicated before, zero mean variance sigma square, if we evaluate this hk prime rk inverse hk, whole thing inverted, sigma square over k. And this is what we obtained earlier. So up to now we are just verifying what we obtained before. Now we will rework this batch least squares estimator into the recursive form. So to obtain the recursive form of the least squares estimation, we are going to evaluate the S matrix, which is HPH prime plus R. A little bit of algebra yields us k plus 1 over k sigma square. And again, W, that's a PH prime S, and that gives 1 over k plus 1. So now we can go to the final recursive form of the least squares and obtain the new estimate is the old estimate plus 1 over k plus 1 times the residual, which is the latest measurement, minus the previous estimate, because the previous estimate is the best prediction for the latest measurement. Now, for this very simple problem, we could have taken the batch form and just manipulate it into a recursive form, rather than use the big gun of the general recursive least squares estimation. And let's go through this second way of obtaining the recursion, which is specific to the problem, namely x hat k plus 1 being 1 over k plus 1 sum of zi, I going from 1 to k plus 1. I can rewrite the summation inside as a sum up to k and the last one separate. Then I notice that the sum up to k is really k times my previous estimate plus the new measurement. I will subtract and add the previous estimate, because here I have a k plus 1, here I have a k, so here it's a plus minus 1 here. This k and the plus 1 x hat k cancel with the outside 1 over k plus 1 and give me x hat k, and inside I have the measurement minus the previous estimate would gain 1 over k plus 1. So here's the recursion. It is identical to what we obtained before, and since this is a scalar problem, we can initialize it as the first estimate. We use exactly the first measurement, which is really the best estimate obtained from a single measurement. So this completes now the recursion. Next, we will work out a procedure to use prior information if we have, apart from the least squares. So now we change our model. X is assumed a random variable which has a prior information consisting of a mean x bar and the variance sigma 0 square. We'll cast this problem into the framework of the linear minimum mean square error estimation, and the model for the measurements will be with the noises Wi independent, identically distributed, zero mean with variance sigma square and independent of x. Now, without using a superscript on z anymore, Z is H super K X plus W super K. So this is really a big vector. Now that's the total set of observations. And we can calculate, for the purpose of the LMMSE, the PZZ. This is the covariance, really a variance, because it is a covariance matrix because Z is a vector. Now it's really a stacked vector. So the expected value of Z minus Z minus Z bar transpose, I can write the Z as HX plus W. The Z bar is HX bar. This is the mean of Z bar times the same thing, transpose. Because of the independence between the X, the prior information about X, the prior density of X, and the W's, there will be no cross term, so there is 1 with 1. That gives me HK. This is an identity matrix that I don't have to write down here, X minus X bar, sigma 0 square HK transpose plus I. Now with I, there's a K by K identity matrix times sigma square. So it's a HK X minus X bar times itself, with X bar being X being a scalar. Really, this is just a scalar here. So there's a H scalar H transpose. And similarly, I need the PXZ. That's the covariance between X and Z. This is a scalar, this is a vector. So this is my scalar X minus X bar. Again, Z minus Z bar. The Z is a H X plus W. The Z bar is the H X bar here. There is no cross term. The term between the product between this W and this X minus X bar, after the expectation becomes 0, so all I get is a sigma 0 square HK transpose, because this is a transposition here. And now we need the inverse of what we have in equation 12. We use the matrix inversion lemma again. So the inverse of this matrix is I sigma to the minus 2 minus sigma to the minus 4 over K sigma to the minus 2 plus sigma 0 to the minus 2 H transpose, where sigma is the, or sigma square is the variance of each measurement noise. Sigma 0 square is the variance, the prior variance of that parameter X, a scalar. And the linear minimum mean square error estimate is X bar. X hat K is X bar, the prior mean, plus PXZ, PZZ inverse, times Z minus H super K X bar. So all these terms now are available. They will be substituted, and simple algebra leads us to the expression that the estimate at time K is a linear combination of the prior plus some gain here multiplying the sum of Zi minus X bar, where Zi are the observations, X bar is the prior mean on X. And it can be rewritten as obviously also a weighted combination between the X bar and the sum of the Zi's. These are the weights, and this is our result that shows how to combine prior information, in which case we have to go back and use the LMMSE, but the result is really a generalization of the least squares, the LS result. As before, we will investigate what happens if the prior becomes diffuse. That's just a sanity check to verify that our results are okay. If sigma 0 tends to infinity, the prior information becomes diffuse. There is no information effectively. And we have a non-informative prior or no prior, in which case our combination of the prior information and the least squares boils down to what we already have seen in two different fashions from the least squares result. This is the sample mean. So either least squares or maximum accurate estimate. And this clearly again indicates how we can go at the limit and eliminate the prior information by making its variance go to infinity. Now, here's a real-world example. The real world is not linear in most cases. What we are going to do is a non-linear least squares. What the goal is to estimate parameters from a set of non-linear measurements. This nonlinear measurement problem will be illustrated on an angle-only observation situation for a stationary target obtained from a moving platform at different times. So what we have is there's a target position, x location at psi and eta in the plane. The sensor platform position at time I it's a moving sensor. Remember, we don't have now full position observation. All we're going to do is angle. Really, that's a direction of arrival measurement. So our measurement, Zi, is arctangent eta, that's the y-coordinate unknown location of that object, minus eta platform at I divided by psi minus psi platform at I plus noise at I, which is denoted now by V of I. And these noises are zero mean, white, Gaussian with variance sigma square. So what we have now is a fixed object for which from several locations we measure an angle of the line of sight towards that object. Practically speaking, this can be an optical sensor which just measures the line of sight, or it can be an acoustic sensor. If that object emits acoustic energy, you can measure an angle towards the object from which energy is emitted. So this is really a passive measurement system. Here is an illustration. Assume we have 3 locations of the platform. At each location, we measure an angle. If you had 2 locations, you have a triangulation problem. If you have 3 locations, it's called a multilateration. And hopefully it will be more accurate than the triangulation. Clearly, from a single observation of an angle of the direction of arrival of some energy from some object, you cannot localize that object because all you know it's somewhere along the line of sight or line of propagation of the energy from the object to you. That's all you know. So you need at least one more observation. And the idea is the more you have, the better off you are because you can combine these pieces of information. So what we do now is take a stacked vector of our 3 measurements and write them as a vector h boldface function of x and x platform. We assume we know where the measurements have been taken from. The x platform where our sensor is located is known. Plus the measurement noise, now it is a w vector, a 3-dimensional vector, and the vector h has 3 components. Each depends on the vector x, the unknown location of the object, and our known location. This is a w, this is a v, both, all of them should have been w to be consistent. There are some typos here, sorry. Okay, now, how do we solve? This is a nonlinear problem. If it was a linear problem, we can solve it in one shot, a batch solution, or equivalently, we have an algebraic reworking of the solution into a recursion. Now, if you have a nonlinear problem, you cannot solve it in one shot. So what we do in this case is, if we are given an initial estimate, the iterated least squares technique goes as follows. I have an initial estimate in the iterated least squares after iteration j, say. The next iteration, x hat j plus 1. What we are going to do is we use a recursion within the iteration with a fixed data set. So this is now a batch technique on which we have to iterate because the problem is nonlinear. The J sub j is the Jacobian matrix. This is a vector, this is a vector. If you notice, this is a three-dimensional vector, this is a two-dimensional vector. So the result is going to be a 2 by 3 matrix. The J transpose will be 2 by 3 J's 3 by 2. And we have the Jacobian calculated as discussed in chapter 1. Now, the iterated least squares estimator will progress by applying a correction term to the current estimate based on the measurement residual. The iterated least squares is similar to the recursive least squares, but it really reprocesses the entire data. We have here the Jacobian, this 3 by 2 matrix, and because these are partial derivatives of the arctangent, obviously they are not constant, you will evaluate these always at the previous estimate, and we have the explicit expressions of that of all these derivatives. This arctangent partial with respect to the x or psi component and with respect to the eta component. The initial estimate in this iterated least squares estimator can be obtained from the intersection of any two of the three angle measurements. This is a simple triangulation, and this is easy to obtain using simple geometry and trigonometry. And then we iterate on our ILS until the result converges within a certain accuracy. We just gave in a previous equation, which is the ILS recursion. The way it is obtained is as follows, and that's interesting to see how we solve a nonlinear problem. This is essentially a hill climbing technique. Using a first order series expansion about our, say, previous estimate, I take by z, which is, these are my functions, the measurement functions, which is h of x and xp plus w, now we have the w notation for the noise, is approximately equal to, note that here x platform is known, x, the target, is not known. So we expand this function h about x hat j up to first order. So the function Taylor expansion equals the function evaluated at the point we have a first estimate, our previous estimate actually in this case, plus the first derivative, the matrix form of this is the Jacobian times the difference between the point x and the point at which we are doing, or about which we are doing, the Taylor expansion. So this is the first order Taylor series expansion of a vector function of another vector. This happens to be h is a three-dimensional vector, x is a two-dimensional vector. Now, what we are going to do here is we say that we have an approximation, obviously z minus this h at x hat j, is equal to this first order term, that's the Jacobian times x minus x hat j plus the noise. What is nice about it, this now is a linear least squares problem, so we solve exactly in batch form a linear problem which is an approximation of our original nonlinear problem, because we linearize the nonlinear problem by limiting the Taylor expansion to first order. So, based on this, the solution will be, so we can solve this, we call this the observation. This is a constant, because that's evaluated at x hat j, and we can solve for x hat, that's the new solution, will be x hat j plus 1 minus x hat j is the standard least squares that used to be an H matrix in the batch least squares. So that's the same expression times our measurement. So the measurement is really a difference between how good our previous approximation was and the actual measurements. Now, we can go back and solve the same problem that we had by formulating it as a maximum likelihood estimation, and the numerical search technique can be Newton-Raphson. So the maximum likelihood estimate, x hat ml, will be obtained as usual by writing the likelihood function lambda of x and then maximizing it. So lambda of x in this case is p of zi given x. There are three such zi's, each is a Gaussian. Here is the measurement, here is the dependence of the measurement, the noiseless measurement that we would obtain ideally on the state or parameter we are estimating, in this case, the vector x. So what we are after is an x hat maximum likelihood, which is the argument that maximizes with respect to x, lambda of x, or minimizing the negative log likelihood function, which is denoted by lowercase lambda of x. So this is the cap lambda likelihood function, this is the negative log likelihood function, nothing but the exponent. We don't care about the constant. Now, this is really the same as the nonlinear least squares problem formulation. So we have the same problem, but we'll formulate it in two different fashions, and we'll end up with two slightly different solutions for the same problem. The way to minimize this is numerical search. All nonlinear problems require numerical search. So the previous one, we worked out an iteration by expanding our nonlinear function to first order, and that yielded the iterated least squares. Now we take a maximum likelihood approach, write the log likelihood, negative log likelihood function, which we are going to minimize. So it's really the same criterion, but the minimization technique in this case will be Newton-Raphson. Namely, the new estimate in iteration j plus 1 for the maximum likelihood estimate is the one from iteration j minus, and this is the hill climbing technique, h is the Hessian times the gradient of the likelihood function. This is really the log, the gradient of the negative log likelihood function. So this is another numerical technique, the Newton-Raphson method, that will carry out a numerical search for the extremum of a function.